Hello students. In today's lecture on the principles and chemical applications of thermodynamics, we will continue our discussion on the second law of thermodynamics and talk in detail about entropy. We have already talked about how the Carnot engine introduced to us a new state function called entropy. And we have also been able to evaluate the change in entropy of the system for different processes, where for the sake of simplification, I have used 1 mole of the working substance. Now, if I go ahead and remind you of the different expressions that we arrived at for reversible processes, this is a list of the different processes that we have already talked about. Now, as we understand by definition, for an adiabatic reversible process, the amount of heat exchanged in a reversibly is 0. So, correspondingly, at all non-zero temperatures, delta S is going to be equal to 0. But if I have an isothermal process, then the definition tells us that I can take the temperature to be constant, and delta S turns out to be a ratio of the total amount of heat exchanged between the system and surrounding in a reversible fashion divided by the temperature at which such exchange has taken place. We have also talked about how to evaluate delta S in an isothermal expansion of an ideal gas or isochoric heating of any system. So, if you have a system with both heating and volume change, then you can find the resulting change in entropy as a function of the initial and final temperatures as well as the initial and final volumes. Finally, when looking at heating at constant pressure, we understood that it can involve both a phase change and a heating at constant pressure without phase change. And according to the experimental condition, I will either have some idea about the change in enthalpy during the phase transition at a temperature T, which is a constant during phase change, and then I can find out what the corresponding delta S is. But if the system simply undergoes heating and stays in the same phase, then if I know the specific heat at constant pressure of the system and the initial and the final temperature, I would be able to compute the change in entropy for such a process. So, this slide actually summarizes all that you need to know to solve a problem given that your process is a reversible one. We then talked about how to get the change in entropy for an irreversible process. So, little Calvin, who was introduced to us by Bill Watterson, thought that since entropy is defined in terms of reversible processes, he can do without thinking about irreversible processes. So, he looks grumpy over here. So, what kind of irreversible processes that we have talked about? We have talked about the freezing of supercooled water, and also we have talked about mixing of two ideal gases. And we found that in both the cases, we are able to find the change in entropy between the initial and the final state by constructing reversible steps between the initial and the final state given for the process. Now the next question that comes into picture, keeping all these in mind, is whether we can calculate entropy change accompanying a wide range of change in temperature. Now if you have a pure substance, in that case, you can equivalently say that can I measure entropy at any temperature? So that would mean that, let us say I start from a very low temperature, very close to the absolute zero of temperature. So in most of the common cases, the substance that I am working with will be a solid. Now if I heat this solid at constant pressure, then it is constant heating of the solid at constant pressure. So if I go on heating it at some certain temperature T equal to Tf, the liquid will start melting, the solid will start melting into the liquid. And as you see that here there is a question of not only a heating at constant pressure, but it is heating at constant pressure with phase change. And therefore, when the solid is transformed to liquid at this temperature, the temperature will also remain constant as long as all the solid is transformed into the liquid phase. Finally, if I go on heating even more, then what I would have is heating at constant pressure of the liquid phase. If I continue heating, I will arrive at the temperature T equal to Tb, whereby once again I will have the situation where the liquid will start evaporating. So there will be a liquid to gas phase transition, and since this transition involves some latent heat, therefore at T equal to Tb, when we are heating the liquid, the temperature will also remain constant as long as the liquid is getting transformed into the gas. So here again, I have another instance of heating at constant pressure giving a phase change, whereby during the phase change, the temperature will also remain constant. And if I heat the system further, what I have is the heating of the gas at constant pressure. Therefore, this is what I mean by change in entropy accompanying a wide range of change in temperature. So it means that I'm going to measure the entropy change as I go from a very low temperature to a rather high temperature, and this transition may involve phase transition at different stages. Now, associated with this, as I have already mentioned, we would like to know the measurement of the value of entropy at any temperature. So what I mean by this is, for this process, as I have shown here, I can always calculate delta S. So if my initial equilibrium state was at T equal to 0 and my final equilibrium state is at a finite temperature T, then what is delta S? Delta S would be the value of entropy of the system at the temperature T minus the initial value of entropy when T was equal to 0. Now we have already discussed how to find out delta S for such system, for these kind of processes. Therefore, I can find out S of T, that is the absolute magnitude of entropy at a temperature T, as the magnitude of entropy at absolute zero of temperature plus delta S. Now, as you understand that in this case, I have already discussed how to get delta S for different processes. In this example, I need to know how to calculate delta S at different stages of the transformation from T equal to 0 to a finite T, with and without phase change. Therefore, if I want to know this S of t, I need to now find out what is going to be the value of entropy of the given system at absolute zero of temperature. So this has been actually mentioned over here. So for this process of transition of the solid from T equal to 0, heating of this at constant pressure up to a temperature T, when it is in the gas phase, I know that S of T is equal to S of 0 plus this entire quantity, which is delta S, and I can compute delta S provided I know the heat capacities of the solid, liquid and the gas phase. Also, if I know the freezing temperature, heat of fusion, boiling temperature and the heat of vaporization or the standard enthalpy of vaporization. So, for all these, as I have already mentioned, that experimental data are available in the literature. Therefore, once again, let me emphasize that I can find out the absolute value of S of t, provided I know the experimental data on the specific heats, etc., and the entropy of the system at absolute zero of temperature. Now, so let us spend a little bit of time talking about how to get the absolute values of entropy. So scientists carried out a lot of experiments on systems at very low temperatures, and this is how Nernst gave a heat theorem which summarized a wide body of observation, and it says the entropy change for any chemical or physical transformation approaches zero as the absolute temperature approaches zero. So this means that for a given system, S tends to 0 as T tends to 0, but it happens when all the substances involved are perfectly ordered. So this is what is known as the Nernst theorem. I will give you one typical example of an experimental data that was used to propose this heat theorem. And this corresponds to a structural transformation of sulfur. So S that I have noted down here in the blue color corresponds to sulfur, not entropy. Okay, the blue S is sulfur. The beta form of sulfur is transformed into the alpha form of sulfur, corresponding to which I can write down the change in entropy due to this phase transition would be molar entropy of the alpha phase minus molar entropy of the beta phase. Now, from experiments, it is possible to determine the enthalpy of transition. And it is found that the enthalpy of transition is minus 402 joules per mole at 369 Kelvin. Therefore, this is an instance where I know the temperature of the transition, I know the enthalpy of the transition, so I can immediately calculate the change in entropy during this transition. So now I find that Sm alpha minus Sm beta, that is equal to about minus 1 joules per Kelvin per mole. Now, another set of experiments were carried out whereby one followed the change in entropy of the pure phases alpha and beta separately. And it was found that the molar entropy of alpha, it varies as this, where this is the molar entropy of alpha at absolute zero, and this is the increment in joules per Kelvin per mole as the alpha phase goes from very low temperature to the temperature of the experiment, that is 369 Kelvin. Similarly, the behavior of the molar entropy of the beta phase was also monitored as a function of temperature, and it up to 369 Kelvin, and it was found that this is given by this value of the molar entropy of the beta phase at absolute 0 plus this quantity. So now I can combine these two values and find out what delta S of transition is, which is Sm alpha minus Sm beta. So when I calculate that, what I find is this turns out to be from this estimate, delta S transition turns out to be Sm alpha minus Sm beta minus 1 in joules Kelvin inverse mole inverse. Now let me compare these two panels. Both of them tell me that I am measuring the same thing. The change in entropy during the transition of sulfur from its beta phase to its alpha phase at 369 Kelvin. Now, if I compare these two, I can equate this quantity to this. So, what will it mean? It would mean that Sm, that is molar entropy of alpha at 0 temperature, minus molar entropy of beta at 0 temperature is nearly equal to 0. And not only that, if you look at the amount of change over here, you would immediately conclude that the molar entropy of each of these phases at 0 temperature is a very, very small number, from where it was argued that the entropy of these systems would approach to 0 as T tends to 0. From here, the third law of thermodynamics was formulated, and that the statement is including the what we have discussed in the previous slide. It says the entropy of all perfect crystalline substances is 0 at T equal to 0. Now you understand that we indeed required an additional law of thermodynamics to tell us about what happens to S at 0. Now that you know S at 0, you can definitely find out S at T, which would be equal to S at 0 plus delta S, where you can find out delta S for the process that you have designed to take your system from very low temperature to very high temperature. So this is the way you can find out the absolute value of entropy at any given temperature, where you have learned about delta S from the second law of thermodynamics and S of 0 from the third law of thermodynamics. And some of the third law entropies at standard state at 298 Kelvin, these values are shown here. As you see that this value, this is the molar entropy at 298 Kelvin, these are very different for different quantities. And as expected, the solid has a much lower value of the entropy, standard entropy at 298 Kelvin. The liquid water has somewhat larger value of entropy, and then if you look at another water like benzene, another liquid like benzene, it is a lot more. And finally, if you look at the gas phase, you find that the standard entropy value is much, much more than any of these systems. Now, from our understanding of what these systems differ by, we understand that the solid is an ordered structure, this order decreases in the liquid and is minimum in the gas phase. And therefore, I would say that if I go from the gas to the solid, this is the direction in which the underlying structure would have higher degree of order, and therefore we associate the concept of entropy with the degree of disorder. And our conclusion would be, as disorder increases in the microscopic structure at the thermodynamic level, that is at the macroscopic level, this would be demonstrated by an increasing value of entropy as we go in the direction of increasing disorder. Now you might wonder that how do I compare the two cases of water and benzene? Here both of them are liquids, but water has a much lower entropy than benzene. As you understand, water is a very interesting system because of one property that it possesses that liquid benzene does not, and that is the hydrogen bonding. So because of the presence of hydrogen bonding at the microscopic level, there is more order in water structure at the microscopic level in comparison to the microscopic structure of benzene. Of course, there is no hydrogen bonding by the standard definition in liquid benzene, and therefore I would say that water is expected to have a lower value of standard entropy at 298 Kelvin because of hydrogen bonding, which makes it more ordered. Therefore, if I go from water to benzene, the disorder increases in the microscopic structure and the entropy also increases. So the take-home message from this slide is, if I want to find out the absolute value of entropy, so in that case, what I need to do is I need to use both the second law of thermodynamics as well as the third law of thermodynamics to find out the absolute value of the entropy. I cannot do so in terms of the second law of thermodynamics only. So this brings us to a conclusion of this slide, that now if instead of the solid I have a perfectly crystalline solid, then I will not have any contribution from S0, and correspondingly I can find out what the value of S of t would be in terms of the delta S, which I have already mentioned, that can be measured in terms of experimentally determined quantities like specific heat of the solid, liquid and the gas. In addition, you would require information about the enthalpy of fusion and vaporization, as well as the temperatures at which the melting and the vaporization takes place. So with this, now let me show you that I posed certain key questions about entropy. And what we found is that the first question that we posed was, can we estimate the change in entropy for different processes? We have explained to you in detail how to do so. And in addition to this, we also talked about how to use the second law and the third law of thermodynamics to evaluate the absolute value of entropy at a given temperature. The next question that we posed was, how is entropy used to predict the direction of a spontaneous change in state? And then if I have the system arriving at a new equilibrium state, what would be the condition that would determine that a particular state is going to be the new equilibrium state. And finally, we also wanted to understand how entropy helps us in understanding why we never have an ideal heat engine. So far we have talked about the first question. Now in the next lecture, I am going to talk about this very important question as to the use of entropy to predict the condition of spontaneity and equilibrium as a macroscopic system passes from an initial equilibrium state and proceeds towards a final equilibrium state and then equilibrates in that final state. Thank you.